So with that, let's get to the fun stuff. So I'm very excited today to welcome Angela Koo to give the JQI seminar. So she is at the University of Illinois, Urbana-Champaign right now. She did her PhD work with Charlie Marcus and Amir Yacobi before going on to a postdoc with Michel Devereux. And so she works in all kinds of interesting superconducting qubits, and I will let her tell you all about it. Bailey, can I put it here?
Yes.
Super.
Okay, cool. So thank you for that nice introduction, and thank you for having me. I'm very excited about the conversations that we're going to have today. So what I'm going to discuss today is some of our work trying to figure out how to build better superconducting qubits, and the people doing the work are the grad students that are shown here. And so this talk is going to be about quantum computing, and if you've read the news recently for like the past decade, that you've seen articles on quantum computing, I like to check in on what the current hype about quantum computing is. And then so these change every so often, but right now, so people think that quantum computer powered robots are going to overcome humans. It's going to be bigger than AI. This was actually from like last week. It's going to solve climate change, and it will also help you beat cancer. So actually, these articles change every like few months. So I encourage you to Google this and look at this. So there's always, I think, for as long as I've been in the field, and that's not as long as a lot of us have been in the field, there's always been some hype about quantum computing, but we're still not yet at the point in which we have useful quantum computers, and the Financial Times is actually correct. The quantum computing is struggling to reach its silicon moment. Despite the fact that we've heard about these recent breakthroughs from Amazon and Microsoft, we're still a long way from building practical machines. And then so what I'd like to talk about today is what are the limitations that we're facing, and what are some of the approaches that might help in order to get us closer maybe to the silicon moment and get us closer to building a quantum computer. So I'm going to focus mostly on superconducting qubits. That's where I can have some reasonable contributions to it, but I think some of the things that we're facing in superconducting qubits also affect other platforms. Okay, so to understand the limitations, what we can first think about is what do we need from just a qubit? So a qubit is this two-level system. We can characterize all the states that are possible from this two-level system using this block sphere. And the first thing you want from a qubit essentially is the ability to perform initialization. So I want to be able to put it in some sort of state. Let's say we're going to characterize it by psi of 0. And I want for it to basically remain in this state forevermore. I want to know the Hamiltonian such that I know how it's going to evolve. So I want initialization first from my qubit. The next thing you want from your qubit is the ability to have some single qubit control, right? So if I want to use this as some sort of building block for a computer, I want to be able to perform gates. I want to be able to control the state of this qubit and where it's going to go, okay? And then the next thing you want from a single qubit is the ability to perform a measurement, so that when I'm done with my single qubit control, let's say I put it into the 0 state of the qubit or the 1 state, so one of these poles, I want to be able to perform a measurement that assigns the correct value. So when you perform the measurement, it tells you that you're in 1 if the qubit is in 1. And if you perform a measurement, it tells you you're in 0 if the qubit is 0 and not the wrong thing. So these are the kind of 3 things that we want from single qubits. To build a quantum computer, having single qubit control is not that fun. So what we want from a quantum processor is actually to have a large number of these qubits. And then so we want to be able to initialize all of them. Then we want to be able to perform our single qubit gates, but also 2 qubit gates. And this is where the power of quantum information comes from, right? This ability to do entanglement and to do multi-qubit control. And you want to be able to do a sequence of these single qubit and 2 qubit gates. And then you want to be able to perform a single qubit and multi-qubit measurements on your qubits that are part of your processor. So this is what we want from our quantum processor. And if we lived in an isolated world, if these qubits were by themselves, this would maybe not be so hard, right? We can manipulate things if we could manipulate things pretty well, if we can build these kinds of qubits, this is not so difficult. But we don't live in an isolated world. These qubits don't live by themselves. They're surrounded by an environment that's constantly introducing errors to the system, right? So there's all kinds of different things minions that are trying to ruin our computation in all kinds of different ways. And as we actually make our qubits better, we find always new ways in which our system can be getting worse, right? And then so there's all kinds of things that are possibly trying to ruin our computation. Maybe they're not even trying to ruin our computation, but they somehow ruin it, right? Okay, so in the face of us constantly being surrounded by errors, we can think about what kind of error threshold we can try to we can live with, right? So the environment is constantly doing something. We're fighting the environment, but at some point we're not going to be able to, we're not going to build perfect qubits. So we need to figure out what is a level that we can deal with in terms of these errors. And an often quoted level is to think about when we can start to do quantum error correction and when this quantum error correction becomes useful. And so if we think about quantum error correction, so we are going to say that we can tolerate some level of error. So for classical computers, this is also true. You decide you can tolerate some level of errors and you use error correction. So here for quantum error correction, the idea is that we encode our qubit in a series of physical qubits. So we call the kind of larger qubit the logical qubit, and we have some physical qubits that we encode in. And then so if an error arises in one of the physical qubits, we can make the correct kinds of multi-qubit measurements so that our logical qubit is no longer affected. So this allows us to deal with some amount of error in our system. Okay, but even to get to quantum error correction, your physical qubits need to be at some quality. So for different quantum error correcting codes, you can have different thresholds of error that you can tolerate in your physical qubits. And an often talked about error correcting code is the surface code. And there's some level of error that's associated with the surface code. So we can walk through this plot here. So the idea is that if your physical qubits have an error rate that's on the order of 99%, then you can start to do this error correction where your logical qubits should work better than your individual physical qubits. But if you're exactly at the threshold, the number of qubits to actually get some low error rate in your logical qubit is going to diverge. And then but if your qubits get better, so that if the single step error rate decreases, then you can use a fewer number of qubits to achieve some logical error rate. And so we probably don't want to be at this 10 to the minus 5 level. If I gave you a regular computer that had errors at the 10 to the minus 5 level, you would throw that computer away. So we probably want to be much closer to this 10 to the minus 10 or 10 to the minus 20 for the error rate of your logical qubit. Okay, so this gives us some idea of a threshold that we want to get to in order to build some number of qubits. And we can trade the number of qubits that we have for the single step error rate to try to achieve some error in our logical qubit to try to build this quantum computer. And so we can think about where we are currently in quantum computing in terms of the hardware that we've developed. And then so currently in most platforms, I would say we're at kind of this level. So at the 99.9-ish% level. And then so what this means that if I want to get 10 to the minus 5 error, I'm going to need about 100 qubits. If I want 10 to the minus 20, then I'm going to need about 1,000 qubits in order to actually make quantum error correction useful and have a logical qubit that has this error rate. Okay, so you could take two approaches at this point. You can say, okay, I've already gotten below the threshold. Now all I need to think about is just scaling the number of qubits that I have, right? I just need to increase the number of qubits. As long as I can keep this amount of error by increasing the number of qubits, then I'm totally cool. I can build my quantum processor. So you can take two approaches. Different people like different ways. But the thing is, it actually turns out to be very difficult to keep the same error rate as you increase the number of qubits. And then you can think about this kind of each qubit has its own little error problem that it comes with. But when you start to couple them together, you create new error channels that are present. You create new error channels that are present, right? Because now they're coupled to each other and they can have crosstalk. And then so you end up with this kind of whole system of problems that arises. And then so in actuality, this is I'll show a plot later showing what happens. But if you actually look at how our scaling is actually doing, so this is now for superconducting qubits specifically. I don't exactly know how it's going for atoms. But for superconducting qubits, what you have is that, so in like 2014, there was the first kind of error correction, and then the rate at which we're increasing this number of qubits. So it's been an order of magnitude over the past roughly 10 years, which is already like extremely impressive and awesome. But if you actually want to build something that's useful in terms of quantum computing, this trajectory needs to go much better, right? And so what we need, I think, is both. So I think we need both better qubits and also better scaling approaches to actually try to get to this kind of utility scale quantum computing.
Now there's
Yes.
a dotted line there with a legend that's illegible.
Okay.
So tell us what's going on with those dotted lines.
Okay, yeah. So this kind of area is the kind of current pace, let's say, at which we're going with what the technology that we have now, if we kind of just roughly scale where we're going. So these are this line.
Yeah, the lower ones is where we are now, you're saying.
This lower one is, okay, so this is the trajectory that would correspond to this slope here. So like if I had followed, if I decide from error correction to quantum supremacy, like if I had followed this trajectory, it would have been this line.
Right.
But the actual trajectory is kind of this line, so it's going like this. So actually, from 2014 to 2018, we were pretty, I guess people were more optimistic, and then so we would have gotten better. But the real trajectory, as we're getting a larger and larger number of qubits, is actually slowing down. So that's what this kind of white area says. The industry expectation, always high expectations, is here. And then so to actually meet that expectation, you need a much, much steeper trajectory. So, I mean, you know, we can make, maybe one day we can make quantum computers, but if we go at the current pace, I might be super old by the time this happens.
Yeah.
We all might be super old by the time this happens.
You know,
I'm on Zoom. I wanted a clarification. Yeah, the desired trajectory, is it dictated by Shor's factorization algorithm, or what are the types of problems?
I think there are multiple different kinds of algorithms you can consider for a quantum computer. So there are algorithms for kind of optimization, and also algorithms for kind of simulation of molecules. And then so I don't think that it needs to be exactly Shor's algorithm, but I think they have also similar requirements for the things that they want. And then so I think that's what we're looking for in terms of utility scale quantum computing. Oh, sorry. Yeah. Okay. Sorry, I didn't repeat your question. The question that was asked was a while ago was what is shown here in this plot, basically.
so you're thinking you're kind of on the pessimistic side.
I think I'm realistic. I would say realistic. If I were pessimistic, I would probably not say we need better qubits and better coupling approaches. I would say I should work in a different field. But I think that I think it's not, I mean, I think it's really cool that we've been able to get to where we are. And I think that it's also really awesome in terms of research to be able to say like, oh, we can think of new ways to build qubits, new error correcting codes that we need, and also like new ways of coupling the different qubits together to try to make this kind of what we think is an amazing thing happen. So
Okay, so I'm going to ask you the following question publicly. I asked this a lot.
Okay.
People. I got a bet with Carl Williams that the question is, by the year 2045, when I certainly expect to be dead, will we have a quantum computer that can factor numbers that a classical computer cannot factor in a year? Which side of that bet do you want to be on?
2045 is in 20 years.
Yeah.
How big is the number that we have to factor?
That cannot be factored by a classical computer of that time in 1 year.
And how much are you betting?
I'm going to put up, you know, how much you're betting shouldn't it?
If you bet $10, I'll definitely be on the other side of the bet.
It's gonna, well, you know, and it's gonna be thousands of dollars, and we're gonna try to get other people to chip in, and it'll be a scholarship for a young person or a prize.
Yeah, sure. I'm happy to be on we'll do it by 2045.
Okay, so you want
I'm happy to be on the other side of this bet.
So you're on the optimistic side of that bet.
Yeah. Also, you said it's only thousands of dollars, so.
Why much it is? Which side of the bet you want to be on?
Okay. Yeah, go ahead.
So Sunny, you have the top optimistic or goal is like 1 million qubits that I have. Does that account for the limitations of size and wiring? Like, is 1 million superconducting qubits on a chip?
Oh, this doesn't have to be on a single chip. It's just, this does not have to be on a single, no, there's no reason. It's just the number of qubits that you can use for computation.
Okay.
Yeah.
We're not at a point where we can couple multiple chips on between
I will talk about this later.
different.
That
I
plot
think you can divide the computer into
likes to
modules.
talk about reality. Let her keep going.
Yeah.
Okay. So this is the outline of my talk. So I guess we sort of understand a little bit the problems now that we're facing in qubits. So I want to talk about our ideas for improving physical qubits, also some of the problems that we're facing in terms of measurement. This is something that I think more and more people in the field are currently focusing on, and understanding how to make measurement better is really important for building a quantum computer. And then also how to make off-chip connections instead of just having on-chip connections. And if there's time, which I now no longer think there will be, I want to talk about some material science stuff that we're doing to make superconducting qubits better. Okay, so first we're going to talk about improving physical qubits. So we've talked generally about qubits, but I wanted to just show you some of the details of the things that we're working on. And the things that are specific to superconducting qubits. So in superconducting qubits, we basically have 3 circuit elements in our toolbox. So we have a capacitor, inductor. These are linear elements. And to build our qubit, we need something that is nonlinear. So this is a Josephson junction. And these 3 components, we can control the charging energies, inductive energies, and Josephson energies to kind of basically make tailored artificial atoms. So by changing these different values, I can change what the potential looks like. So this is the potential energy of, let's say, this circuit as a function of the phase difference across this Josephson junction, which is related to the flux that's in parallel with the junction. And so if I change the shape of this potential, then I can change what the energy structure looks like. And then, so depending on what purpose you want to use your artificial atom for, you can tailor the potential energy and the energy structure. And then I would say that this is kind of one of the powers of superconducting qubits, is that you have the ability to change your circuit elements and tailor them to make for the purpose that you want to use them for. So you can build amplifiers, you can build different things for quantum simulation, you can also build different kinds of qubits. So that's what we like about superconducting circuits. And then so just to show you what they kind of look like in terms of scales. So for our superconducting devices, our capacitor will look something like this. The scale is on the order of hundreds of microns. We can make inductors that are thinner and smaller. So these are on the order of 3 microns, and our junctions can be on the order of micron and also hundreds of nanometers. So this is what the individual physical components actually look like. For the capacitor and the inductor, we can make these out of different kinds of superconductors, niobium, tantalum, different materials. For our junction, though, we mainly use aluminum and aluminum oxide junctions. This is kind of the only material systems that we know that we can control well enough to build these kinds of superconducting circuits out of. And the 2 leading qubits currently in superconducting devices are the transmon and the fluxonium. So the transmon is a Josephson junction in parallel with the capacitor. The potential energy for that circuit is shown here. By changing the Josephson energy and the charging energy, you can change this anharmonicity. You can think of this transmon as an anharmonic oscillator, so it's very lightly nonlinear. And the transmon regime is where the Josephson energy is much larger than the charging energy. So this is quite a simple circuit to build and understand. It's probably the most prevalent superconducting circuit. But the issue is that because it's only lightly anharmonic, it can be very easy to couple it to non-computational states. And then so if you maybe try to drive this transition too fast or too hard, then you can end up going into higher level energy states, which you don't typically want. Okay. And the other kind of leading superconducting qubit currently is the fluxonium, which is composed of a Josephson junction in parallel with a capacitor and a large shunting inductance. And the energy eigenstates are determined by this superconducting loop here. And then so the eigenstates are persistent current states that flow in different directions. The fluxonium is typically operated at a location where the potential is shown here. So you have 2 degenerate wells. And then so the eigenstates are superpositions of persistent current flowing in the circuit. And then so this is a more complicated circuit than the transmon. And so fewer people work on it, but more and more people are starting to work on it now. And this is actually the qubit that I'm going to focus on for this talk. This is what my lab kind of specializes in. And so we like the fluxonium because even though it's more complicated, there are additional knobs that you can tune. So I can change all these 3 different energies to try to decrease unwanted couplings and tailor the fluxonium to be what we want it to be. Okay. And so in reality, what these things tend to look like, so this is the transmon, there's a junction located here in the center, and then you have the capacitance located here. And for the fluxonium, the inductance is quite large, and then so it's made by using a kinetic inductance of a superconductor, and that's in parallel with a Josephson junction, which is then also in parallel with a large capacitance here. And then so these two qubits currently have single qubit and 2-qubit gate fidelities greater than 99%. So they're pretty good. They're on that line that I showed you before in terms of the kind of thresholds that we're looking for. And then so, but we did talk about the fact that we maybe want to make better qubits than what we currently have, right? And then so we can think about what is currently limiting these qubits. And so I'm going to use the fluxonium as a test case. It turns out what I'm going to say is also usually true also for the transmon. So for the fluxonium, you can get relaxation time up to 1.6 milliseconds. This is not average, so this is kind of the best, and a coherence time that's on the order of 1.5 milliseconds. And for the superconducting qubits, what limits us is not control, but really these lifetimes and coherence times and the rate at which we can perform our gates relative to these lifetimes and coherence times. And then so if you look at this, you might be able to actually guess what is currently limiting the fluxonium. So we have these large metallic pads and a lot of metal that's located on top of a very clean substrate. And then so what's currently limiting the fluxonium is relaxation due to dielectric loss. And so this is an experiment that was actually done here in Maryland in 2019, where they looked at the relaxation mechanisms of different frequency fluxonium and found that it fell very well on this line that corresponds to dielectric loss. And then so if we think about what causes relaxation and how you might get rid of it, so there are two possibilities. So one is making the material better. So this is the noise spectral density of the material at the frequency of your qubit. So you might think about making your noise spectral density better, or you can try to design your matrix elements of your qubit so that the transition rate is lower. Okay, so yeah, go ahead. We operate at 10 millikelvin, so we think the phonons are not super active. We do have, the phonons would affect like quasi-particles in our system, and then so that is a problem that superconducting qubits is generally facing now, that there maybe are quasi-particle excitations that then excite photons and cause loss. But that's not kind of included here. We're mainly limited right now by this dielectric loss. Yeah. Oh, sorry. For online people, the question was, how is this dielectric loss, how is the system affected by photon loss? Yeah.
How much of the loss is from the junction oxide and how much of it is from the substrate?
In this, it's mainly, well, okay, so it depends on the design, what the participation in, sorry, the question was how much of the loss is from the junction and how much of the loss is from the capacitor or substrate, I guess. And then so it depends mainly on the participation ratio. And then so for these kind of 1.6 millisecond, like the higher levels of loss, that's mainly due to this kind of substrate. But for if you have like kind of slightly lower, that you can get participation from the junction as well. Okay, so I'm not a materials scientist right now, but so what I think of when I'm trying to design for better is I can just purchase the best materials that I can, but I can try to design my circuit to be less sensitive to this noise. And the way that we would do that is to try to localize the system better, right? So if I have disjoint qubit states, then this matrix element can become smaller, and I can try to engineer myself into a better regime. And indeed, if you simulate what happens, if you look at, so by actually changing the charging energy and making it smaller, you localize your system much better and localize your eigenstates much better, and you can make the T1 extremely long. So that's great. But then if you look at how the frequency changes as a function of the external parameter, which here we use the flux through the loop of the fluxonium, it gets much sharper and sharper. And this is not great because it means that our dephasing from Lex noise is going to increase, because the dephasing of the system depends on the derivative relative to this whatever noisy external fluctuation there is. And you kind of can't win in a system that has a single degree of freedom, because for making relaxation better, we want disjoint states, but for making the dephasing better, we want actually delocalized states. So in your single degree of freedom system, you kind of always have this trade-off between making something disjoint versus making something delocalized. And then so, I mean, the solution is to try to make something with more degrees of freedom. Yeah, go ahead.
Sorry, are you always operating at pi external?
Yeah, we always operate at half flux to try to be insensitive to the question is whether we're always operating at half flux. So we're always operating here because of the derivative, you will always be sensitive to flux noise. So we try to operate at the sweet spot. Yeah, okay. So we always have this trade-off between dephasing and relaxation. And then so in single degree of freedom systems, so we want to try, even though it's a little bit more complicated, we want to see if we can kind of make qubits that might be better with more degrees of freedom. And then so this is an idea that's, of course, like all things, because I was one of the first people to think of this idea. And then so the idea is to try to have more degrees of freedom to engineer protection. If you actually kind of think about it, it also is kind of related to quantum error correction as well. So the idea here is that we can, if we have 2 degrees of freedom, I can choose one axis to perform, to use to localize my states, make them disjoint. And then I can choose another axis, the delocalization axis, to try to make the dephasing long. So I can use the other axis to try to delocalize my system and one axis for localization. And this is kind of the idea behind a lot of kind of new protected circuits that are coming out now. And so we would like to consider kind of the simplest system that we can think of that has 2 degrees of freedom. And then so that is the fluxonium molecule. And then so it becomes a little bit more complicated, right? So now we have to control 2 Josephson junctions. We have multiple inductors that we have now to control. And then so the Hamiltonian for the circuit is shown here. So we have the Hamiltonian, the terms associated with single degrees of freedom, and then there's just one coupling term here that we now need to consider. And then so for this kind of system, I can think of what the wave functions as a function of the phase difference across this junction and this junction look like. So that's shown here, the wave function as a function of the phase difference across the right junction and the lower junction. And then you can end up, so now we have 2 degrees of freedom, so we have these 2D plots. And the wave functions can get localized if we bias at half flux again in different wells, right? And then so if I choose the ground and the excited state for this system, so just the lowest 2 energy states, I have delocalization, but actually they're not disjoint. So I still will be sensitive to kind of T1 losses. And we measured this kind of when I was a postdoc. And we did see that the qubit states are delocalized, but then it was still limited by some, T1 was still limited, and then you were also limited by differential mode flux noise. But this is actually still turns out to be a pretty good circuit. We don't necessarily need to throw it away because we do see that there are eigenstates that can be disjoint, right? So if I chose one set of states from one of the states from this set and one of the states from this set, I do end up with now disjoint, right? So I can choose either G or F or G or H or E or F or E to H, and then I have disjoints, which should allow me to have long T1, and they're still delocalized, which should allow me to have long T5. Okay, and then so let's say we choose G to F as our eigenstates, but one problem still remains, right? They're very far in energy. And the fact that they're very far in energy means that then now I can end up with some problems where this energy difference is affected by some external parameter. So I want to try to make it seem as if they're much closer in energy. And in superconducting qubits, we have another thing that helps us, which allows us to, we can apply very strong drives to the system. And then so we can, instead of using this instead of using this fluxonium molecule, we can make a Floquet fluxonium molecule. So we can apply a strong drive to the system to bridge that energy gap and bring the 0 and 1 states close together. So if I now look at the wave functions corresponding to this Floquet fluxonium molecule, what I end up with are exactly the eigenstates that I want. So I can have my 0 be these states and my 1 be these states. And then actually these 2 states become what are known as erasure states. And in quantum error correction, it turns out that if one of the errors that mainly affects your system is an erasure error, that it has a much better threshold compared with kind of relaxation and dephasing type errors. And then so you can build this this is kind of what we think would be a very good device to start to build and try to build a better superconducting qubit. And then so we can actually numerically diagonalize the system and calculate the kind of expected dephasing rates for different types of flux noise. So now we have this two qubit composite qubit system. So it is sensitive to kind of differential mode flux noise and common mode flux noise. So what's plotted here is the minus log of the dephasing. So brighter is better as a function of the applied drive amplitude and frequency. And then so you can see that if you just apply basically any drive that's kind of close in frequency to the G to F transition, you can improve both the dephasing rates for this kind of system. And if you end up in kind of the optimal line, which is shown for both of these, you can have vastly improved dephasing rates compared with not applying a drive. So that was something that was really cool for us. Yes, go ahead.
A lot of problems with these Floquet systems have to do with interactions, coupling in the pumping.
Yes, very good. So what you see here, this is a numerical diagonalization. So what you see is there are some places where you have things that look like this. This laser is very non-specific, but you see there are these things here, right? So this corresponds to accidental degeneracies where your drive maybe is running into energy levels that are not the ones that you want to couple. And then so you can incorporate, you can kind of see this when you're numerically diagonalizing the system. So you can see what places you actually do need to, I mean, to do the experiment, we'll just avoid them. But you can actually predict where these interactions will start to take place. Yeah, so it looks like there are large regions of phase space in which you would not be driving these accidental, let's say, degeneracies that one typically worries about in Floquet systems. Yeah, any other questions? Yeah. No, it's robust against a lot of, so it doesn't require fine tuning is what I want. Well, okay, so it requires fine tuning in the sense that you need to be able to get your frequencies at the kind of megahertz level and your amplitudes, but this is kind of well within our capabilities in terms of the electronics that we have. And then the devices can be, they don't have to be exactly the same either. So your junctions don't have to be the same. So this is why we kind of liked this system, because it doesn't require a lot of fine tuning. It doesn't require some extreme parameter regime either. Yeah. And so we can try to take into account all the possible loss mechanisms that arise from. So if we apply now a strong drive, you can see that this number now gets a little bit lower. And this is because now we are also thinking about if we apply our drive, if there's some amplitude noise or frequency noise from our system, how that would affect. And then so this decreases it down to 4.4 hertz. And then we can also calculate what the relaxation rate for this kind of qubit should be and what the erasure rate for this qubit should be. And you can see that it's dominated by erasures, which is good for error correction. And we can kind of theoretically, what we expect in terms of T1 and T2 is kind of way higher than our average superconducting qubit can be. Yeah.
What do you mean by you're dominated by erasure errors? I see that rate is actually smaller than
so this plot was generated by theorists, and then so it's minus log. So high, like this, brighter is better, and then so it's more likely to have a erasure error compared with gamma 1 and gamma 5.
How would it be just use the ground and excited state of fluxonium without?
Yeah, so that's closer to like the standard fluxonium times. Yeah.
Around a millisecond or something.
Okay, so I would say the best fluxonium is around the millisecond. The average fluxonium is probably a few hundred microseconds to a millisecond. Yeah. Yeah. Okay, any other questions?
So I'm a little bit confused about going from gammas to T's. So
Just 1 over.
Okay, so there wasn't any magic there.
No.
Okay. Okay, so there's a star and gamma. Wasn't sure what that was about.
The star refers to no echo, so doing just a Ramsey sequence to get the
Okay, so that's actually a T side
by star.
star.
Yeah.
Okay. Now, one more thing, because some
Yep.
of my colleagues are just waiting for
Sure.
it. As
Waiting for me to build this qubit.
as a defender of the SI, I have to tell you, I implore you, never to use Hertz or the decay rate, because Hertz
Okay.
can only be used for periodic phenomena.
Okay. Okay. You're gonna have to.
The theorist, it's not her.
Yeah.
Well, over there on the other side, there's a gamma that's Hertz.
No, but okay. Yes. Okay, good. Okay, so we're very excited about this and we're building this now in our lab. So, but we think that hopefully this should lead to kind of significantly longer expected coherence times and a better hierarchy of error channels. And so we're starting to build this now. Okay, so this is kind of the way, I just wanted to show you that this is kind of the way that we think about trying to build better superconducting qubits and what we think will help in terms of making our currently existing qubits better. Okay, so the next thing I'm going to talk about is something that is maybe less positive, but also I think very interesting, which is how we do measurements in superconducting qubits. And I'm very far. I mean, I might not get to the third part of this talk, but that's okay. Okay, so we can think about what we want for our measurement requirements, right? So if I have some I have 2 qubits here, and maybe what I would like to do is actually, let's say in the middle of a computation, so we need this for error correction, but maybe also for algorithms. In the middle of a computation, I need to be able to perform a measurement. And then I need to be, and I don't want that measurement to affect my qubits, right? So I want to be able to do some multi-qubit measurement that doesn't change the state of my qubit. And then I can use the information that I find from my measurement to determine how to manipulate the qubit later. So this is what you typically want for quantum error correction. You may want this for algorithms as well. Okay, so for these 2 things, what I want is the measurement to reflect the state of the qubit. I want the assignment fidelity to be high. And I also want quantum non-demolition. So the measurement commutes with the qubit Hamiltonian. So my 2-qubit measurement, let's say, commutes with my qubit Hamiltonian so that it doesn't affect the qubit later when I perform my measurement. Okay, these are the 2 things that I want. And measurement also needs to be as good as our gates, right? So when we talk about, a lot of the times when we talk about these kinds of things, we mostly focus on gate fidelity, but measurement fidelity also needs to be much, much greater than 99% when we're building our devices. And so in superconducting qubits, the way that we perform measurement is we do something called dispersive measurement. So we couple a superconducting qubit to some linear resonator, and then we end up with this Hamiltonian that is here. So this is some qubit Hamiltonian. I have some qubit Hamiltonian, and then I have some the term that corresponds to my resonator, and then I have some coupling between my qubit. We're using charge here, so we have some coupling between the charge operator of the qubit and the let's say X component, the real or the imaginary part of my resonator. Okay, and we typically operate in the dispersive regime where the coupling strength is much smaller than the tuning between the qubit frequency and the resonator frequency. So I end up with this kind of nice dispersive Hamiltonian where the frequency of the resonator depends on the state of my qubit. And this is the standard way in which we perform readout. This is called dispersive readout. And so that if I monitor the state of my resonator, so this is now the imaginary, the in phase and the out of phase quadrature of my resonator, depending on the state of my qubit, the response of my resonator will change. Okay, and then so if my qubit is in the 1 state, I might get something that is located here. If my qubit is in the 0 state, I might get something that looks like is shown here. And then you can see that this Hamiltonian, my measurement commutes with my qubit Hamiltonian. I just have the sigma z term. And then so I can observe quantum jumps, and it shouldn't, when I perform my measurement, it shouldn't affect the state of my qubit. So quantum jumps of superconducting qubits have been observed, first observed in 2011, and this is something that we use. This is our standard way of performing readout. It's known as dispersive readout. The best superconducting qubit assignment fidelity currently is 99.75% in 100 nanoseconds. As I mentioned, we want to be much above 99%, so we want to try to do better. And so the way that you might think of trying to do better is I can try to improve the signal to noise ratio. So I can try to put more photons in my resonator to separate these two blobs more so that I can better assign what state corresponds to which resonator response. Okay. This, people have tried this and it runs into problems. So I mentioned that we want both high assignment fidelity and also quantum non-demolition measurements. And when we put more photons into our resonator, what we run into is that the quantum demolitionness gets worse. And so this is an experiment with a transmon where you can think of quantum non-demolition as if I start out, if I measure that the qubit is in some state and then I measure again, does that qubit stay in the same state? So you can think of that as a way for a proxy for figuring out how Q and D the system is. And you can see that for a transmon, so this is a measurement. As you increase the number of photons to above 10 to maybe try to increase this assignment fidelity, that quantum non-demolition goes down to 0. So that is very, very bad. And there's now some theory that recently some theory to try to understand where this comes from. And it actually does come from that leakage to higher energy states in the transmon. In the fluxonium, it's been much less measured, but also there do seem to be real problems with QND-ness. So you get a 25% reduction in the relaxation time of your qubit when you're measuring it. So that's also very bad because your assignment fidelity scales basically exponentially with the T1 of your system. Okay, so we wanted to understand what are some of the limits on the fluxonium, and then so we did this experiment, so I'm going to talk about now. And then so we built this circuit, so standard circuit that I just showed, where you have a fluxonium that's capacitively coupled to a resonator, and we measure the response of the resonator. So the fluxonium is shown here, so there's a small junction. This forms the inductance, and then there's a capacitive pad that's shown here that couples to this coplanar waveguide resonator. And then so the experiment that you can do to understand what is limiting the quantum non-demolitionness of the system is shown here. So we initialize the qubit in some sort of state. We make an initial measurement to tell us what state did I start out in. I can put in a fake kind of proxy readout tone that mimics a measurement and changes the number of photons in my resonator. And then I can do a second measurement to see how well it stayed in the first state. So my final measurement is actually a little bit stronger and a little bit longer, but so that I can kind of assign the states a little bit better. So if we put no photons in this proxy kind of readout, you can see that it basically not much changes. So we still have similar numbers of counts in the ground state and the excited state, and there's not different effects. We don't see kind of this quantum non-demolitionness. So good thing I don't put any photons in my resonator where my qubit doesn't really decay on the time scale at which we're measuring. So that's good. Now I can try to mimic a tone where I do have mimic a measurement tone where I do start to put photons in my resonator. And so if I put 15 photons, you can see that the non-QND-ness has already started to take hold. And so if I take my initial measurement, it looks something like this. Now if I put 15 photons in and take a second measurement, what I see is that the populations in the ground and the excited state are different. Bad. And also I start to get another response in my resonator. So this means that something is happening when I'm taking my measurement to change the state of my qubit, right? So it's becoming quantum non-demolition. And then so I can do this experiment at multiple different photon numbers. So that's what's shown here. And then I can plot the probability of if I start in the ground state, what is the probability that I stay in the ground state? And then if I start in the ground state, what is probability I end up in the excited state or end up in some other state? And then so here you can see that. So when I start out, it's kind of at 0 photons, there's some T1 decay on my measurement. So it's not exactly at 1. But as I increase the number of photons for the ground state, it seems reasonably okay. It still comes down, but it's kind of staying pretty well above, let's say, like 80%. But at the excited state, it's actually really bad, right? You can see that starts to get below 50% for a small number of photons, this QND-ness, and then it kind of stays fairly low as I increase the number of photons. So that's really not great. And then so you can we can kind of take a page from the transmon idea of what's happening and think of, oh, maybe what's happening is that when I have my qubit states in the ground and excited state, when I send in my photons to read out, I'm actually accidentally exciting from my qubit state to some other states. And then so I can model this kind of system. It's not super difficult. So I have the fluxonium Hamiltonian, the resonator Hamiltonian, and I can add a drive term. Okay, so if I add the drive term, this actually, when I diagonalize this, I can exactly figure out which state I'm going to. I know that the ground to excited state is actually forbidden, cannot be driven by this resonator, but the excited state can be driven. And then so the theory for this kind of drive is shown here in the dashed lines. You can say it sort of reasonably predicts this decay for the ground state, but for the excited state, it drastically kind of underestimates how bad the QND-ness is going to be. And so we need to add something else to our model that is that kind of models that the system is getting worse. And then what we can kind of see is that we added an extra kind of spurious system that is coupled to our fluxonium and resonator. And what we find, and the spurious system we say is a two-level system that we don't know the origin of. And what we think can occur is that when you add photons into the resonator, it also shifts the qubit frequency by this kind of chi value, and then creates accidental resonances with the spurious mode. And then if you add this in the model, it fits actually pretty well. And so this is telling us that our resonator drive is not just inducing transitions to other states, but it can also bring us on resonance with spurious modes. Yeah, go ahead. Yeah, very good. So we can, if you change the flex of the system, you can change the selection rules, and then so the ground state becomes much more affected by this this drive that can send it to higher levels. But there might be another TLS that's present because we just have these material systems that we don't control super well, and then so you can run into other resonances as well. And then so you can see that the shape kind of changes. So in dotted here is in dotted here is the response at half flux, and then at as we move farther away, this shape changes as well. And then, yeah, go ahead.
So if you think this is some spurious system, you run the experiment like 2 weeks later or like after cool down,
Yeah.
and so on, get something completely different.
Yeah.
Right.
Yeah. So you have to change the so the ground state response is actually mainly due to Hamiltonian dynamics, so that doesn't really change. But the excited state response does change a lot because this spurious system is just like moving around and we don't really control it. Yes. Yep. Yeah. Yep.
Do you have any insights about the frequency spectrum of these TLS? Like at what frequency there are more than?
Okay. So TLS is a name for it's just a name. We don't even know if they're TLS. Right? So the frequencies, we don't know this frequency spectrum. This is something that's like an active field of research right now to understand what is the origin of these defects and where they come from. So we don't know if it's kind of a white spectrum or whether there's some thing in which they cluster around. So this is an open question. Okay. Any other questions? Okay. Okay, so but with this kind of model, we kind of understand what is causing problems in our system, right? So we can start to think about are there ways we can design around it? It's hard to design around something you don't know. But what you can do is you can try to optimize your readout by, let's say, changing the resonator frequency. So our qubit design is chosen so that we can optimize T1 and T5. But then we do have freedom of how we couple the resonator and the frequency at which we change the resonator. So you can, using this model that we think well represents what is happening in the system when we start to read out our qubit, you can start to kind of try to design around it. But what we see is that so this is the shift on the resonator depending on the qubit state, and you can change this number by changing the resonator frequency as a function of number of photons. And what you can see is that the QND-ness stays pretty good if you have a lower number of photons, and if you have a lower kind of, let's say, if we have a lower chi, then the QND-ness also kind of stays really good. But if you run into spurious modes, which are shown here, well, this is Hamiltonian dynamics, so you can try to avoid this. But if you run into a spurious mode with your excited state, then you end up with huge problems in terms of QND-ness of the system. And then so they're difficult to account for, and we'll probably need to think of other ways of reading out our superconducting qubits that are not standard dispersive readout is kind of the conclusion that we're coming to. And it means that we need better approaches and different approaches for superconducting qubit readout. And we also, if we could figure out the two-level system or materials, let's say the defect problem, that would also be a huge help for superconducting devices. Okay, I don't think I actually don't think I have time for this last kind of section. I'll just give you kind of the upshot. So I talked about how if you connect qubits, the system actually turns out to be worse. And so this is a computer science paper where they looked at the architecture of different sized devices. So this is the controlled X infidelity of different sized IBM processors. So you have 27 qubits in red, 40, I can't even read this, sorry, 65 qubits in blue and 127 qubits in green. And then so you can see, so these are box plots. So the median or the average is shown here, and the max and the min is shown here. So you can see that for smaller numbers of qubits, you actually do better in terms of infidelity. So you want to be low here. And so what this tells us is that we're going to need to have multiple qubits on a single device, but you probably also want to think about making inter-chip connections really good when you're designing the architecture of a processor. Yep.
Why does the red infidelity go down?
Why does the red infidelity go down? Or are you asking why it's lower or whether?
Yeah, it goes back down. Like it goes up and it goes down.
So this is just as a function of time. This is just measuring on different days. So it.
Oh, okay, so it's not like an ongoing. Like.
No, I think the fact that it's fluctuating is just due to the process. Maybe the processor was fluctuating on different days. Yeah. And then so what this kind of tells you is that you maybe don't want to make a huge chip with a million connections. You maybe want to make it into a more modular type of system. Okay. Okay, so I think I'll maybe just kind of talk about this and then, okay, so for superconducting qubits, the way that we can do this is we typically connect some sort of cable bus or resonator between two different systems. And then so here, this has mostly been done with transmons, so just a junction parallel with a capacitor. And then so what people have done is the transmons are kind of located here and connected them via a long fiber or via some cable bus. Actually, this is super amazing. This is two dilution refrigerators that are connected via a 30-meter tunnel at 4 Kelvin. So this like waveguide is held at 4 Kelvin to do kind of build this modular architecture. And then you can get swap error rates that are on the order of 1%. And this limitation is based on the lifetimes and also based on how strongly you can drive this kind of swap transition between the different devices.
Were these bridges set up for this experiment?
Yes. Actually, this is like a super impressive feat of engineering, and
Just be a loophole-free belt.
yes, it is a loophole-free belt test. This is what it's mainly been used for. Yeah, but right, and then but you need to kind of be able to do 2-qubit gates in order to do the kind of loophole-free test. Yeah. Right. So you can get swap error rates on the order of 1%. This is limited by the fidelity of the qubits, but also by the rate at which you can kind of drive the system. And in the transmon, I mentioned that you can have kind of leakage problems. So the fluxonium is, you can possibly think of using the fluxonium to kind of increase these swap error rates. And I'm running out of time, so I'm just going to say that we've started to build these kinds of systems, and you can perform kind of controlled release of controlled release of photons from the fluxonium, starting to do these kind of swap operations between the fluxonium and a traveling photon in these kinds of systems. Okay, so I'm gonna kind of skip this, where I'm also happy to talk about material science to try to improve superconducting qubits and try to think of different superconductors maybe that we could also use to build superconducting qubits with. And so hopefully I've shown you some of the limitations and some of the ways in we can try to address the limitations in superconducting qubits and how we can think of ways to get us closer to kind of that utility scale quantum computing. So thank you for your attention. And these are, I.M. and Ka and Matt are the people that have done the experiments and the theory for some of the things that I've shown. And I'm happy to answer any questions that anyone has. Yeah.
So the other new point on that map of the future graph
You started with.
I do not have a new point yet. You have not asked a question yet. Oh yeah, so when you put photons into the resonator, it Stark shifts the resonator, and then so we can measure that Stark shift and also the dephasing rate that it imposes on the superconducting qubit itself. So those two things is how we calibrate the number of photons in the resonator. Yeah, go ahead.
First of all, you say you did engineering Hamiltonian, so like for the qubit, you projected that T1 will be 50 milliseconds down. So what's the cell limit on that, and how do you plan to measure T1 that long?
So our electronic setup is stable for much longer than milliseconds, so that should be totally fine. The other for long T1s, for experimentally, you can do also kind of quantum jump experiments and just look at the rate of the quantum jumps. So then that can give you the T1. And sorry, what was the question before that one? Yes, that's right. Yeah, so here, the fluxonium, you can design the resonator to be very far from the transitions that you're interested in using as your qubit, and then so the Purcell limit is actually quite long typically for the fluxonium.
And the diagram, G to E is very small, but the G to F seems to be very large.
No, the G to F, so relative to the G to E, it's very large, but at the level, it's still like 5 times smaller than the resonator frequency. Yeah. Yeah, go ahead.
Have you thought about how you do qubit case with the fluxonium option?
We've thought about it. I don't know that we've drawn any conclusions about how to actually do that yet. So that's something that's ongoing. We're still working on. Yeah.
Clarification, like this molecule, like is it possible to make like a formal mapping to like error correction control, like define a distance? And if so, like does it make sense to think about like scaling up the circuit?
Yeah, so with quantum error correction, the minimum number of qubits you can do for correcting 2 types of errors is 5 qubits. And then so I think it would be really interesting if there was a way of building kind of the stabilizers into a passive Hamiltonian. The fluxonium, I would say, is probably closer to like a 3, like, if you scaled up, it would be much closer to like a 3 qubit, just kind of classical repetition type of thing. For the molecule, it's just 2 degrees of freedom at the moment. And then so it's not yet at that level, but you can think of increasing and trying to build it. Yeah.
One last question.
I think fluxonium kind of plan to do maybe rotor cones. Yes. But I had a random question about using this readout. I always saw those plots, these 2 plots.
Yeah.
Trying to get. Have you ever tried to do machine learning for that?
So I think people are working on right now.
Yeah.
Yeah.
Right.
I think, yeah, so I think it does help in terms of making the fidelity a little bit higher, but I think that to get like these, let's say multiple orders of magnitude that we want in terms of making measure fidelity better, you can't get to that much using the machine learning. Like, so I think we need to try different readout approaches compared with dispersive readout.
Some of them are really there's a transition during the readout
Yeah.
process, which is not.
Yeah, so it's
separable
yeah, so it's a bad thing because the measurement now is introducing errors itself. So it's the measurement which you're supposed to be using to try to do the correction is actually making the system worse. And then so it's, yeah.
Why don't we take Angela for the